Welcome to Systemic Stack. My name is Kabir Anand. This is episode 23 of the System Engineering series, and today we will explore leader election in a way that helps you prepare for system engineering interviews on this topic. So, knowing how a cluster designates a single coordinator is essential for preventing data chaos and split brain scenarios. In an interview, being able to explain the mechanics of Raft or Paxos shows you've got the depth to maintain consistency and serializable writes when things inevitably go sideways. We begin with the technical chaos that erupts when a distributed cluster lacks a single voice. Establishing why a coordinator is essential for serializing writes and keeping history predictable. This leads into the core process of leader election, where we designate one node as the authoritative source of truth. We'll explore two primary use cases, distributed scheduling and metadata management, to see how a leader prevents duplicate work and keeps the system's view of data consistent. Then, we dive into the heavy hitters, Raft and Paxos. These algorithms are the backbone of consensus, and knowing how they handle votes and proposals is a high-value signal for any system design interview. Once a leader is in place, we'll look at how heartbeats and failover mechanisms manage the transition when that leader eventually crashes. It's also vital to prevent the split brain nightmare, so we'll examine how quorums ensure only one leader can act at a time. By the end, you'll understand how these components weave together into a complete consensus system to keep your architecture resilient and synchronized. You've built a high-scale application with a cluster of 5 nodes. Everything seems fine until two different nodes decide to run the same cleanup task at the exact same time. They both try to update the same row in your database. Or worse, they both try to delete the same file from S3. This is the classic race condition, but at a cluster-wide level. Without a leader, your system is basically a group of people trying to drive a car where everyone has their own steering wheel. It's a mess. In an interview, you might be asked how to scale a task scheduler. If your answer is just run more nodes, the interviewer is waiting for you to spot this exact problem. You need a way to ensure that for certain critical operations, only one node is the boss. The constraint here is reliability. If that boss node dies, the whole system shouldn't just stop. You need a dynamic way to pick a new one without human intervention. That's the real-world engineering challenge we are solving here. Imagine that 5-node cluster again. If every node thinks it's the boss and starts scheduling tasks or updating global counters, you're looking at total chaos. We call this a lack of coordination, and the consequence is usually data corruption or inconsistent state. To keep things consistent, the cluster needs one node to act as the coordinator, the single source of truth for specific operations. Now, why does this matter? Well, it simplifies the architecture significantly. Instead of every node trying to reach a consensus with everyone else for every tiny update, which is incredibly slow and complex, they just talk to the leader. But here's the catch. That leader is a single point of failure. If it crashes and you don't have an election mechanism, the whole operation grinds to a halt. A common failure mode in interviews is forgetting that while a leader solves consistency, it introduces a bottleneck. You have to design the election so it's fast enough that the downtime during a leader change is barely noticeable to the rest of the system. At its heart, leader election is the formal process where a distributed group of nodes agrees on a single master or leader. This node becomes the authoritative voice for the cluster state. It's how we move from a collection of independent actors to a unified system. What matters here is that it creates a clear hierarchy for decision making, which is much more efficient than a pure peer-to-peer model for things like writing to a database. In an interview, you'll want to emphasize that this leadership is temporary. The node is only the leader until it fails or a network partition occurs. One major failure mode to watch out for is the zombie leader, a node that thinks it's still the leader but has been cut off from the rest of the group. If it continues to issue commands, it can cause massive inconsistencies. That's why we use concepts like terms or epochs to ensure that an old leader can't override a new one. It's about ensuring that at any single point in time, there is only one valid authority. Coordination is the secret sauce that makes distributed systems feel like a single cohesive unit. Its main job is to serialize writes and prevent duplicate tasks. If two nodes try to update the same record, the leader decides who goes first, ensuring a predictable, linear history of events. Without this, you'd have to use heavy all-to-all consensus for every single operation, and that just doesn't scale. It's far too slow. By electing a leader, we consolidate that responsibility. However, there's a massive trade-off here. The leader becomes the primary bottleneck for the entire cluster's throughput. If you're being interviewed on system design, you should mention that while coordination solves consistency, it limits how many writes you can handle per second. A common failure mode happens when the leader gets overloaded with coordination overhead and starts lagging on heartbeats, causing the cluster to mistakenly think it's dead and trigger an unnecessary expensive election. Balancing this coordination load is the difference between a stable system and one that's constantly flapping between leaders. Let's look at a practical example, a cluster of workers that needs to run a heavy daily report. If you have 5 workers and no leader and the clock hits midnight, all 5 might try to run that report simultaneously. You've just slammed your database with 5 times the necessary load and you've probably generated 5 identical reports. It's a waste of resources and potentially dangerous for your data integrity. By electing one node as the scheduler, you ensure that the job runs exactly once. The leader is the only one authorized to trigger the task. In an interview setting, this is a great way to demonstrate your understanding of resource efficiency. But consider the failure mode. If the leader fails right as the task is supposed to start and the election takes too long, the report might not run at all. You have to build the system so the new leader can pick up exactly where the old one left off, which usually requires some form of persistent state shared among the nodes or stored in a highly available store like Zookeeper. Think about systems like Kafka or HDFS. They handle massive amounts of data, but someone has to keep track of where that data is. That's metadata management. A leader node, often called a controller or name node, manages the partitions and monitors the health of all other nodes. This ensures that every client gets the same, consistent view of the cluster. If every node tried to manage its own metadata view, the system would quickly fall apart as nodes went in and out of sync. What matters here is that it decouples the data movement from the control logic. However, the bottleneck here is the metadata itself. If it can't keep up with the updates, the whole cluster slows down. An interviewer might ask how you'd handle a massive burst of new partitions. If your metadata leader is the bottleneck, the system can't scale. A critical failure mode is when the metadata leader's storage gets corrupted or its network lags, leading to stale metadata being served, which results in clients trying to read data from nodes that no longer have it. When we talk about how to actually pick a leader, Raft is usually the go-to because it was designed specifically to be understandable. It uses a system of terms and heartbeats. If a node doesn't hear from the leader for a while, it becomes a candidate and asks the other nodes for votes. If it gets a majority, it's the new leader. It's a very democratic, step-by-step process. What matters here is that it provides a clear, provable way to reach consensus. In an interview, you describe this as a majority win system. But the failure mode here is split votes. If multiple nodes become candidates at the exact same time, they might split the votes, so nobody gets a majority, and the cluster just sits there until a timeout triggers a new round. Raft solves this using randomized election timeouts. Basically, every node waits a different amount of time before trying to become leader again. This ensures that one node usually wakes up first and wins the election before the others even start, keeping the transition smooth and fast. Long before Raft, we had Paxos. It's the mathematically rigorous grandfather of all consensus algorithms. It's built around roles like proposers, acceptors, and learners. While Raft is easier to explain, Paxos is what many of the original giant systems like Google's Chubby were built on. It's designed to ensure agreement even in incredibly unreliable networks where messages can be lost, delayed, or reordered indefinitely. What matters here is that it's the gold standard for correctness. However, the trade-off is extreme complexity. Implementing Paxos correctly is notoriously difficult, and many early versions had subtle bugs that only showed up under rare network conditions. In an interview, mentioning Paxos shows you know the history and the deep theory. But you should also acknowledge that most modern teams prefer Raft or specialized variants because they're easier to maintain and debug. A failure mode in Paxos implementation is often livelock, where two proposers keep preempting each other, preventing the system from ever reaching a final decision, effectively stalling the entire cluster indefinitely. Getting elected is only half the battle. The leader has to prove it's still capable of leading. This is where heartbeats come in. These are small, periodic messages the leader sends to all the followers. It's essentially the leader saying, I am still here and I am still the boss. This constant pulse is what keeps the cluster stable. If the followers stop receiving these heartbeats for a predefined timeout period, they assume the leader has clashed or been partitioned away, and they'll immediately trigger a new election. What matters here is that it's our primary mechanism for fault detection. However, there's a delicate balance with the timeout duration. If the timeout is too short, a tiny network blip can cause a false positive, leading to unnecessary elections that disrupt the system. If it's too long, the system sits idle for ages before realizing the leader is gone. In an interview, you'll want to discuss this trade-off between availability and stability. It's a classic tuning challenge in distributed engineering where you're adjusting for network jitter. When that leader does eventually fail, and in distributed systems it will fail, the system enters the failover phase. This is the transition where the cluster detects the loss and promotes a new candidate. The goal is to do this without losing any data or violating the consistency rules we've worked so hard to establish. This is critical because the faster and more reliably you can failover, the higher your uptime or availability will be. In an interview, this is where you talk about the recovery time objective or RTO. A major failure mode during failover is when the new leader isn't fully caught up with the old leader's state. If it starts taking new commands before it has finished syncing the old logs, you end up with a hole in your data history. This is why protocols like Raft ensure that only a node with a sufficiently up-to-date log can actually win an election. You're trading a slightly longer election time for the guarantee that the new leader won't accidentally revert the system to an older state. The absolute worst-case scenario in leader election is split brain. This happens when a network partition cuts the cluster in half and both sides think the leader on the other side is dead. If both sides elect their own leader, you now have two nodes claiming to be the boss of the same data. They'll both start accepting rights and your data will diverge into two conflicting histories. It's a nightmare to fix. To prevent this, we use quorums. A leader must have the support of a strict majority, more than half of the entire cluster to act. Since you can only have one majority in any partition, you can only have one leader. This is a crucial point for interviews. You prioritize consistency over availability in this scenario. The failure mode of a quorum system is that if you lose too many nodes, say 3 out of 5, the remaining 2 can't form a majority. Even though they are healthy, they can't elect a leader and the system becomes read-only or goes offline entirely. That's the price you pay for guaranteed consistency. It's important to remember that leader election isn't just an isolated trick. It's a core component of a broader consensus system. These systems are designed to ensure that even when nodes fail or networks act up, every healthy node eventually agrees on a single value or a specific sequence of events. Leader elections of the whole cluster. Since the leader often has to wait for a majority of followers to acknowledge a right, one or two slow followers can create a significant bottleneck for the entire system's latency. So, we've broken down why leader election is the secret sauce for keeping a distributed cluster from falling into total chaos. The big takeaway here is that having one authoritative voice prevents double scheduling and keeps your metadata consistent. In a design interview, you'll want to highlight that this isn't just about picking a boss, it's about consensus. We looked at Raft's terms and heartbeats versus the rigorous foundations of Paxos. We also covered how those heartbeats act as a life support system. If they stop, the cluster does a failover to keep things moving. By mastering these three components, consensus algorithms, health monitoring, and split brain prevention, you can confidently explain how to maintain a single source of truth even when the network gets messy. That's how you build a system that's both predictable and resilient, right? That's a wrap on leader election. Well, you've now got the tools to explain how heartbeats and quorums keep a cluster sane. In an interview setting, focus on the trade-offs of your design choices. For instance, explaining why a specific timeout length matters for balancing fast failover against system stability is a huge signal. Make sure you can justify why a majority quorum is non-negotiable for avoiding split-brain scenarios. So for more deep dives, go ahead and subscribe. In the next episode, we will discuss distributed locking, where we will discuss situation, core understanding, purpose. Happy system designing.